Dear students, we have discussed already magnetic force on a charge, Lorentz force, Oersted experiment, and the magnetic force experienced by a current carrying conductor in the earlier sessions. Today I am going to discuss the path traced by the charged particle in different situations in terms of angle between the direction of motion of charged particle and magnetic field. There comes three cases. First case, when a charged particle like proton, alpha particle or electron moves perpendicular to the magnetic field. First case. Case 1, when charged particle moves perpendicular to magnetic field. Moves perpendicular to magnetic field B. So here magnetic field is denoted by symbol B. So that's why I wrote B. So it means the field is perpendicular. Okay, let me take the magnetic field here like this. So this indicates the magnetic field is normal into the plane of board or plane of paper. Magnetic field is pointed perpendicular to the magnetic board and inwards, normal inwards. Normal outward dots we represent to represent the field. So this is the magnetic field B. X mark indicates, we can also circle it. Okay, not necessary, but you can put. So this represents the magnetic field into the plane of paper or board perpendicular to it. Yes. Okay, then next. Now if I take a charged particle at some point here. Here there is a charged particle Q having a charge Q. It is directed this way. Its velocity is this way. Direction of the charged particle is this way. So magnetic force experienced by the charge F equal to Q times V cross B. This is the formula. According to this, assume that the charge is positive. Time being, charge is positive. It can be negative, then we have to reverse the force, direction of force. That's it. So when V, charge is positive, velocity V and B, cross product we have taken. So field inwards, velocity like this. See, I will take cross product of V and B. So velocity is right side. I use this fingers easy for me. This thumb represents the velocity vector, first vector. Then the magnetic field inwards, so I use the forefinger to represent the field inwards. Then the force experienced is this way. This is the force, magnetic force experienced by the charge upward, this way. Now when the force is upward, the charge is experiencing a force at every moment of upward direction. So what happens to the charge? It gradually moves upward like this. Like this it goes. Now at every point we can apply this rule, and I will take at this point. So velocity vector, remember always in circular motion, whenever a charged particle moving in circular motion or at any point of journey, the velocity of the particle is tangential to its path. Tangential. So the velocity is tangential at this point. Now at this point, what is the direction of the velocity? Upward. Now we have to find out the force. Okay, like this. At this point I will take the direction of velocity this way. Now you see, velocity first vector, magnetic field inwards, so force is towards the left. So V is thumb, B is this forefinger represents the magnetic field inwards. So the middle finger represents the force acting on the charged particle this way. So at this point the charged particle experiences a force towards left. So now because of this force continuously acting on the charge Q, this will describe a circular path like this. So circular path of radius R. So radius of the charged particle describing circular motion, uniform circular motion it is in the magnetic field. Whenever the charged particle moves, describes a circle. Okay, so then velocity we know, magnetic field applied also we know, then we know the charge q. We have to find out the expression for the radius of the trajectory of the charged particle. Radius of the trajectory of the particle means how much radius it will describe. That radius depends on velocity, depends on mass of the charge, depends on magnitude of charge, and depends on the magnetic field. Okay. So now we have to derive the expression for the radius and angular frequency of the charged particle. So now here what I do firstly, so there will be two forces. So the charged particle describes circular motion only when there is some centripetal force acting on the charge. In first year you have studied that whenever a particle is moving in circular motion means there will be a force. That force is called the centripetal force. We have seen in the case of planets moving around the sun, there also centripetal force is there. That centripetal force is provided by the gravitational force for the planets to move in elliptical orbits. But here the charged particle describes circular path, circular motion. It is because of the magnetic force. Magnetic force is providing the necessary centripetal force for the charged particle to move along this circular path. So therefore the centripetal force required, okay, centripetal force we have studied, FCI, right? If the charged particle has a mass, it may be a proton, it may be an alpha particle or any other particle, it has got a mass. So centripetal force is mass into acceleration. Centripetal acceleration you have studied, okay, so AC. So mass into acceleration. So that mass equal to acceleration of the centripetal acceleration is given by v square divided by r. So r is the radius of the charged particle describing the circular motion, this radius of the trajectory. Okay, so mv square by r, this is the centripetal force required for the charged particle to describe the radius r when it is moving with the speed v. Okay, magnitude of velocity is v. Now the magnetic force experienced by the charge. So magnetic force is equal to Fb equal to QVB sin theta. QVB sin theta. So here observe one more thing. The velocity vector is in the plane of board, whereas the magnetic field B is perpendicular to the board. Velocity vector is in the plane of board always at any point of the charge. So here it is like this. The charge is moving with the velocity vector this way and the force will be downward. And here if I take the charged particle is velocity downward, force is towards the right. Okay, so magnetic force Fb is towards the right. Then now theta value, here theta value, velocity angle between, so this if I expand QVB sin theta, the magnetic force of the charge QVB sin theta is equal to 90 degree. Velocity vector and magnetic field, that angle is called theta. So velocity is along the direction of the board, always it is lying on the plane of board, whereas the magnetic field inverse. So the angle between velocity vector and the magnetic field is always 90 degree. At any point of its circular motion, the velocity vector of the charged particle and magnetic field applied inverse into the plane of board, they are always perpendicular. Hence theta is angle between V and B, always 90 degree. So sin theta equal to 1. When theta is 90 degree, sin theta is 1. Hence the magnitude of magnetic force on the charge is Fb equal to QVB. That's it. QVB. Okay, this one I will take as equation 1, this one I will take as equation 2. Therefore, what happens now? So from 1 and 2, from equations 1 and 2, 1 is the centripetal force mv square by r. 2, equation 2 is Fb equal to QEB. Okay, so mv square by r equal to qvb. So now we have to rearrange to get the expression for the radius. So what I am doing is expression for radius. Expression for radius of the trajectory. Radius of the trajectory of the charged particle. So now we have to get the expression for radius. So we have to simplify. Say here v square is there, and this one v and one v cancel out of v square. So mv remains here. So mv and bring the qb to the LHS. So qb equal to radius. Hence you can write radius of the trajectory. It is not radius of charged particle. Charged particle is extremely small. The radius of the trajectory may be few centimeters. Charged particle size, if it is proton, it is of a few Fermi. We are not telling the size of the charged particle. It is the trajectory. The path traced by the charged particle is circular here, and the radius of such circle is radius of the trajectory, not radius of a charged particle. That just be careful while writing the answer. So radius r equal to mv by qb. Radius r equal to mv by qb. So this is about the radius. Now we have to get the expression for frequency and angular frequency. So frequency omega we have studied in first year in rotation motion. So we know that. So expression for frequency, right? Expression for omega, angular frequency. Okay. So this is angular frequency. Then we can write for frequency and also for time period. Angular frequency omega. Okay. So we have studied in first year V equal to R omega. V equal to R omega. Correct? V equal to R omega in first year. For a rotating body, the magnetic velocity is equal to radius times the angular frequency omega. Therefore, angular frequency omega equal to V by R. Omega equal to, just take R to the other side. Omega equal to V by R. Here R equal to mv by qb. So but R equal to mv by qb. R equal to mv by qb. Thus what happens? I want V by R, omega expression I want. So what I have to do? V by R means I have to take R to the RSS and bring qb and m to the LHS. That is, I rewrite this, take qb to the LHS, qb, then m to the LHS, so qb by m equal to V by R. Say R equal to mv by qb, we have derived here in this. Then I want omega expression for angular frequency of the charged particle. So qb by m I write, that is equal to V by R. Thus, I can write V omega equal to V by R. Omega equal to V by R means that is equal to qb by m. Omega equal to q by r, that is now V by R equal to qb by m. Okay, so this is the expression for the angular frequency. Now angular frequency we got. Now frequency we can get easily. So frequency nu equal to 2 pi frequency omega equal to angular frequency omega equal to 2 pi nu. Therefore this implies that frequency nu equal to how much? Frequency nu equal to omega by 2 pi. So omega divided by 2 pi. Okay, substitute this omega value here, qb by m divided by 2 pi. So qb by m, that is omega value. Then whole divided by 2 pi, that 2 pi goes along with the m. Okay, so qb by m divided by 2 pi. Okay, so then I get it is qb by 2 pi m. qb by 2 pi m. This is the expression for the frequency of revolution. What does this frequency signifies? Frequency says how many times the charged particle moves in this circular path in 1 second time. In a second time, 1 second time duration, how many revolutions does this charged particle completes It may come fraction also. Okay, if it is 10.5, 10 and a half revolutions, you can say frequency is 10.5 hertz. But it will be for if you take photon or alpha particle, all that, in a certain magnetic field, it comes to few megahertz or gigahertz. It is extremely large, and radius may be few centimeter or few millimeter for that charged particle trajectory. Then lastly, time period. This is the expression for the frequency of the revolution of charged particle. Now time period is how much? Time period equal to reciprocal of the frequency 1 by nu. T equal to 1 by nu, that is equal to 2 pi m upon qb. 2 pi m upon qb is the time period of revolution. Okay, time period means what? The time taken by the charged particle to complete one revolution. Assume charged particle starts from this point and goes like this, goes like this, goes like this, and reaches the same point after some small duration of time. That duration of time to complete one revolution is called as time period. Time period expressed in seconds, whereas frequency expressed in per second or hertz. Whereas angular frequency we represent radian per second, or sometimes just hertz. Okay, so that's about the these three derivations. That is for a charged particle moving perpendicular to the magnetic field. When charged particle moves perpendicular to the magnetic field, that discharge, the trajectory is circular. The charged particle goes in a circular path of radius r with a constant speed v in a magnetic field perpendicular to the motion of the charged particle. So that's about the terms radius expression. Radius means how big radius it describes in that circle. Okay, what is the radius of the circle which is described by the charged particle? Then angular frequency omega expression, that is qb by 2m. This is the qb by m omega, and frequency is qb by 2 pi m. And lastly, time period, how much time it will take to complete one revolution in the charged magnetic field, 2 pi m by qb. You might be remembering that the 2 pi term is very common in time period expressions. Okay, so the 2 pi is a most common term. Now we go to the second case, when the charged particle moves parallel to the magnetic field or anti-parallel to the magnetic field. So parallel to the magnetic field means the magnetic force experienced by the charge. Second one, when charged particle moves parallel to the magnetic field. Okay, so this case, so parallel to the magnetic field, that means see the diagram. Let me show the diagram. Okay, so here is the magnetic field. I will show like this. This is the B. If I project a charged particle of charge q and mass m along this direction at the velocity v, then what happens to the trajectory of the charged particle? So the formula for the magnetic force Fb equal to qvb sin theta. This is the magnitude of the magnetic force. Now see, velocity vector v like this, and magnetic field is also same way. V and V are parallel. When V and V are parallel, so theta equal to 0 degree. Okay. Or another case, if the charged particle moves opposite to the field. If the charged particle moves opposite to the field. Okay, this is one case. Now the field is like this. Okay, charged particle I will project opposite to the direction of the field. This is the direction of the charged particle. So it is exactly opposite. When it is opposite, so the angle between velocity vector and the b vector, I can take 180 degree. In both cases, sin theta value turns to 0. Okay, sin theta is 0. Just remember, it is just 0, where these thetas are angles, 0 degree or 0, 180 degree, pi radian we can see. So then what happens to the magnetic force experienced by the charge? magnetic force experienced by the charge is QEB sin theta. So that is QVB into sin 0. Correct? Sin theta is sin 0 is 0 or sin 180 degree also 0. Hence the magnetic force experienced by the charge is 0. That means the charged particle does not experience any force. Then what happens to the charged particle? It does not experience any force. It will continue to move in its original path. So charged particle moving like this, it will go like this. It will not be deflected any direction. It will go straight in the direction it is moving. It is already moving in a direction, so it will continue to move in the same direction. Newton's first law. Whenever there is no net force acting on the charged particle or any particle, any body, it will continue to move in the same state of rest or uniform motion with the same velocity or same speed. Same thing happens, the charged particle will not be deflected either this way or this way or this way. No deflection at all, no deflection, no force experienced. So it continues to move in the same path. Hence the trajectory of the charged particle in this case, whenever it is parallel or anti-parallel, both the cases, theta equal to 0 degree or theta equal to 180 degree. In both the cases, the trajectory is very important here. In all the three cases, trajectory is straight line or linear. Trajectory of the charged particle is straight line. When theta is 0 or 180, the path in which charged particle moves is straight line in the magnetic field. When theta equal to 90 degree, the trajectory is circular or circle, straight line or linear. Okay, you have to say straight line or linear. That's it. Then another case is that other than these three angles, theta is not equal to 0 degree, theta is not equal to 90 degree, theta is not equal to 180 degree. It can be any other angle. Then we have to get the expression for the pitch and radius of the trajectory. So that I am going to discuss in the next class. So here two cases I discussed, and in the first case I discussed radius, expression for the radius, angular frequency and time period. And in this case the force experienced by the charge is 0, hence it will not be deflected anyway whenever it is moving in the direction of the magnetic field or when the charged particle is moving opposite to the direction of the magnetic field. So then trajectory in such case is a straight line or linear. Okay, it will not be deflected anyway. So that's all about these two cases. The third case again derivation is there, so it will take a little more time. So I will do it in the next class, maybe tomorrow or day after tomorrow. That's it.